Thank you very much, everyone. I'm so excited to be back again for this year's conference. And I'm excited to get the chance to speak about something that's been on my mind. I'm a huge fan of AI, as I'm sure many people here are too. I love what I can do with it. But what is the environmental cost of this amazingly cool tool? I see headlines about how data centers are contributing to climate change, but are those blown out of proportion? And is there anything that I can do about it? Today, I want to answer those questions with some real numbers for you. And a bit about my background. I've been in data science for about 10 years, always with a strong focus on machine learning. And now I'm not just a data scientist, I'm a software developer and marketing and sales and everything else, starting my own company and doing consultancy work. I'm the author of 2 O'Reilly books, Software Engineering for Data Scientists that came out in 2024 and Building Machine Learning Pipelines that came out in 2020. Sorry for the feedback, I'm not sure where that's coming from. Get closer. I'm juggling the clicker and the microphone. Okay, is this better? Awesome. So before I went solo, I was a principal data scientist at SAP Concur. And a long time before that, I was a geophysicist at an oil company. And that's really what's motivated me to put this talk together. Because at the time, back in 2012, I was a struggling geology graduate, and I wanted to do something that at least was useful because the world runs on oil. But these days, that's not something I'd feel okay about, working to increase oil production. So when I started getting into using AI, and it became obvious that it was going to be such a big thing, I wanted to know if I was going down a similar route and getting into an industry that was going to be very harmful for the planet. So that's why I put this talk together. In the first half of this talk, I'm going to talk about the scale of the problem. I'm going to put together some numbers on energy usage, water usage, and carbon emissions, and explain the limitations of what we know right now. And then, in the second half of the talk, I'll move on to what we can do about it, strategies that we can use to reduce the environmental cost of the AI that we're using. Here's the there we go. Here's the first statistic for you. I have a lot of statistics for you. I'm sure you're going to love it. In 2024, data centers accounted for 1.5% of world electricity usage. So a lot on a global sense, but it's still, there are many, many industries contributing a lot more. And approximately 13 to 15% of this was accounted for by AI in 2024. It's hard to know exactly how much it was because companies don't share a lot of details, which I'll talk about more later. So this is just a proxy based on the electricity consumption of GPU-accelerated servers. And data center electricity usage is growing at 15% every year, which is fast, but slower than the growth of electricity usage from electric vehicles and air conditioning. And these are old numbers. They totally don't take into account the growth in Agentic AI, but that's what we've got to work for at this point. And I'm not even going to go into this in this talk, but I do notice that we're not even talking about the other 85% of data center electricity use, and if there's anything we can do to reduce that. AI energy usage is growing rapidly. Global data center electricity is currently at 415 terawatt hours per year, but it's projected to reach 945 terawatt hours per year by 2030. And this would be just under 3% of projected total global electricity use. And just to put this into context, that is greater than Japan's total annual electricity consumption. And then AI is projected to grow to 28% of the overall data center usage, according to some Goldman Sachs research from last year. But more recent research this year puts it at more like 35 to 50% of data center usage. And looking at the carbon emissions of the energy used by AI, well, today we think it's approximately 180 million tons of carbon dioxide, but projected to increase to 500 million tons by 2035. And to put this into context, the International Energy Agency estimates that total global carbon emissions are 38 billion tons per year. So it's not the biggest source of carbon emissions, but it is sizable. And unfortunately, this projection may be outdated because numbers are still from last year, pre-Agentic AI. And there's also a move to new data center demand being met by fossil fuels. So headlines like this are not going to help. We keep seeing news articles like this. This is just from a couple of weeks ago. So these emission statistics are probably going to be pretty outdated at this point. Moving on to water usage, this is something that you'll hear a lot about, but it's one where I really struggle to find accurate statistics to put together for this talk. It's all over the place. It depends exactly how you measure this, whether it counts that the water is returned to the local system, and so on. But the best research I could find was a peer-reviewed study from January this year that estimates that AI systems may have consumed between 312 and 764 billion litres of water in 2025. And the upper bound on this is close to the world's annual consumption of bottled water. Why so much water? Data centers are using water primarily for cooling processor chips, and AI workloads are really intensive for this. Another impact that AI workloads have is carbon emissions from building the hardware that AI runs on. In 2024, this was 1.2 million tons of equivalent carbon dioxide, but that's projected to increase to 19.2 million tons, so over a 16 times increase in 6 years. And this is because AI workloads are tough on hardware. GPU-accelerated servers are obsolete in 2 to 3 years, but general servers last 5 to 7 years. So that was the big picture, the overall statistics on looking at a global level. But next I want to zoom in and look at the details of AI's energy usage and what's contributing to this picture. First, I want to look at model training. There's very little published on this from the main providers, so OpenAI, Google, Anthropic. But this is an interesting data point for comparison. GPT-3, which was released in 2020, took just over 1,200 megawatt hours of energy to train it. And this is from the original GPT-3 paper. But GPT-4 training was estimated at around 50 gigawatt hours, so a massive increase, around 40 times more energy for a state-of-the-art model in 2020, in 2023, compared to a state-of-the-art model in 2020. But this is not confirmed by AI, and not confirmed by OpenAI, and we have no idea how much energy more recent models have used for training because there's no data available. What about at inference time? What happens when you send a query to a model? If you're just using it for chat, what's the energy usage there? Well, we have some numbers on this, but take them with a grain of salt. The ChatGPT number is based on a tweet from Sam Altman, and that's the only thing that OpenAI has given us. But they're pretty aligned. A short message uses around 0.3 watt hours. But a long context query, if you were to drop a long document into a chatbot, that uses a lot more. So there's an estimate from last year that if you drop a 75,000 word document into your chatbot and you ask some questions about that, or you ask to summarize, that's about 40 watt hours, a lot more. And I want to talk a bit about agentic coding, because that's one of my main use cases for AI. And this is similar to a long context query. It's a lot closer to that than it is to a simple chat request. And Simon P. Couch, who is a heavy Claude Code user and works at Posit, he gave us some real session data. He analyzed it and found that a typical Claude Code session uses about 40 watt-hours of energy. And he estimated that on an average day, he used 1.3 kilowatt-hours. And to put that into context, average Seattle household energy usage is 20 kilowatt-hours per day. So if you're using agentic coding all day, that's adding over 5% to your daily household usage. Oops. But that's not the way many companies use agentic coding. The token maxing trend that you might hear about in the news is really going to bump up those numbers. And according to this New York Times article that came out in March 2026, there was an engineer at OpenAI that processed 210 billion tokens, or enough text to fill Wikipedia 3 times in 1 week. So I don't even know how much that energy that's going to take. But yeah, these are big numbers. This is not helping. One problem that I kept running into time and time again when trying to put this talk together was that companies just are not releasing data. And that's a problem because it means we can't make properly informed decisions. Many of the statistics I quoted are from over a year ago, and that's not my failure to research anything. The companies are not telling us anything. According to a Stanford report, all 10 major AI companies scored 0 on key environmental disclosure indicators. Anthropic gave us 0 quantified environmental data. OpenAI has no sustainability report, no training data, no emissions figures at all. Google, as a public company, has a duty to provide sustainability reports, but it doesn't separate out AI, so we can't be sure exactly how much of its emissions are due to AI. So that was the bad news. But the good news is that there are things that we, as working data scientists, can do about this. We have leverage here. We can reduce energy usage and without sacrificing the quality of the work that we're doing. And even better, it helps you save money. The biggest impact decision you can make is right-sizing your model. Don't use a sledgehammer to crack a nut. Don't use a big model when a small model will do for your use case. According to a UNESCO report that came out last year, smaller task-specific models can cut energy usage by up to 90%. And if you're building your own system, you can check out the relative energy usage of open source models from this really cool leaderboard from Hugging Face, the AI Energy Score. And this rates 150 models from 1 to 5 stars for inference. And it breaks that out by task. So you can look at text generation models, you can look at image generation models, summarization, and then look at the relative energy usage of all of those. And you can, it's very small print on here, but there's a 62 times difference between the highest and lowest energy models in this class. Unsurprisingly, smaller models are more energy efficient than larger models, but also newer models tend to have a lot of efficiencies relative to older models, so definitely worth upgrading where you can. And if you're looking at production APIs, then cost can be a proxy for energy usage. And using models with lower API costs also means that you're using models with lower energy usage. For example, here's cost comparison between the various different Claude models. Haiku costs 1/5 of what Opus does. So if you can solve your problem with that, go for the smaller model. Another interesting thing that I found out was that reasoning is a huge multiplier on energy usage. And reasoning models use 100 times more energy on average than the non-reasoning equivalents. And this is from the report from Hugging Face that they used to build the AI energy score that I referenced earlier. And you can also think about right-sizing your model if you're writing code with AI. And this is one pattern I use a ton. Plan with a large model, such as Claude Opus, and then implement with a smaller one, such as Claude Sonnet. Then you get the benefits of the large model that has the better understanding of your entire code base. But the smaller model is completely competent enough to write decent syntax and complete the task. There's other efficiency techniques you can play with. One really useful one if you're building chat-type systems is semantic caching. So this is where you store LLM responses and retrieve them for similar future queries. So if you get a lot of the same queries coming over and over, you don't have to regenerate it from the model every single time. And it's great because you never actually need to call the LLM in this situation. You're just calling a database. And you can also think about, if you're developing a prompt where you're going to call an API repeatedly, think about how you can optimize that. If you're just doing a one-off query, probably not worth it. But if you're writing a prompt that you're going to run repeatedly, if you can make it fewer tokens, that's less energy usage. And good practices here are to be specific, structure your prompt well, and try different versions of your prompt until you can get the result that you want with fewer tokens. But you can only make all these changes if you changing to a smaller model, caching, optimizing your prompt, if you know that the new model is going to satisfy your task. So a good evaluation system is what lets you do this. I'm not going to go into details of how to build an evaluation system, but a good way to build this into your system is to start by building a data set, building a gold standard evaluation set. Benchmark your current model, see how well it does on that evaluation set, and then try out smaller candidates. See if they'll complete the task for you. Measure your model performance against the metrics. And if that smaller model completes the task, if it does what you want it to do, deploy that one instead. And as data scientists, I barely need to tell you this, but you need to measure things to improve them. And one really nice tool for this is called Code Carbon. It measures the actual energy usage of your code running on your own hardware. And it's a lightweight Python library that you can install and then just wrap your code in this tracker in a similar way as you might use a timer in Python. There's another tool you can look at, which is called Ecologits for API calls. So you can benchmark from different providers the energy consumption and the carbon emissions across different models. Unfortunately, it's mostly older models at this point, but it's definitely something worth keeping an eye on. So the really nice thing is that green means cheap. When you right-size your model, you're cutting your API costs as well as your energy usage. If you're using semantic caching and 60% of queries hit the cache, those responses are free. When you optimize your prompt, your API bill goes down as well. It's not a tax. It's something that's actually going to pay for itself. And if you go back to your teams and propose these changes, you don't have to bring climate change into the picture if it's not your company's priority. You can frame it as cutting inference costs. The business case and the environmental case are the same. And to sum it up, AI has a significant environmental impact, and it's getting bigger. Carbon emissions are rising, transparency is declining. But there are things you can do. You can right-size your models, you can turn off reasoning when you don't need it, you can cache responses, you can optimize your prompts. And these optimizations compound when you scale them up. Every LLM call counts, and every optimization does as well. Thank you.
Thank you so much.
If anyone wants to dig into more of the details, the top QR code is a GitHub link where I put all the sources for all the statistics in the talk. The bottom QR code, if anyone wants to connect or follow on LinkedIn, feel free.
Cool. I'll leave this up for a second. Does anyone have any questions at all? Yeah? Okay, I'm going to come back to you. Oh, okay, yeah.
Like, I'm not really paying for the cost, the anxiety of the cost, right? So, like, how is that data? Like, who's paying for it?
So, do you mean?
Like, the energy cost, like, who's paying for this energy cost? Is it built into the cost of the tokens? Like, how?
Yes, yes. Unless you're running your own LLM on your own hardware, then the energy usage is going to be paid by one of the large providers, so like OpenAI or whoever. They either have their own data center or they're renting someone else's data center, and then that data center might be run by a different company. They're paying the energy bill. So that's also a bit of a problem because there's a few layers going in to separate you from that. Yeah, thanks.
At the beginning, you said that using a smaller task-specific model cuts energy usage by 90%. Are you referring to building a classical machine learning model, like a tree-based model instead, or are you talking about using a smaller, more lightweight LLM?
Smaller, more lightweight LLM. Yep. It would be really interesting to measure the difference between using a classical machine learning model versus the LLM for the same task. And I think you could do that by using the Code Carbon tool to measure your own model and then looking up the cloud-based model on Ecologits. And that would actually get you a really good estimate of that.
Thank you.
Yeah.
Any other questions? All right, cool. Well, thank you so much, Catherine.